Hello ladies and gentlemen, welcome back to GGS300. So this is essentially the fifth week. It's going to be the fourth laboratory session, and this week we're going to be working on probability. So before we begin, I thought I'd just take a couple of minutes just to look over the syllabus again so you know what we covered, where we're going, and then we can kind of set you up for the midterm exam, which I will set next week when I release the set of lectures. There won't be an assignment next week. There will just be a week to complete the midterm exam. So you can see here, January 25th is when we kicked off, and the first thing we were doing that week was installing R. Week 2 we were then covering introductory statistics, basic R plotting. There was a homework to read this chapter, chapter 2. Week 3 we did descriptive statistics, and there was an assignment set. Week 4 we then did descriptive spatial statistics, and there was an assignment set. That was the assignment 3. And then this week, so the week commencing the 22nd of February, we are working on probability. So the lab session now will be on probability. You'll have the homework, the fourth assignment, and you'll need to make sure that you read chapter 5 and 6. I mean, it's probably worth me stating at this point that I know that this is definitely the hardest week that we've done so far, and I recognise that there's a lot of content that we've had to cover, and there's also a lot of different concepts that you've had to learn. I know that this is really kind of a hard one to get. I would emphasize that it's a really important one to get there, so please make sure that you put the effort in, both to making sure that you do all of the work that I set you here, but also to actually look at some of those other videos that are available online, which kind of give you an overview of how we should understand probability. And it's always useful to look at other videos and other resource materials, because it might just give you a separate perspective that maybe I didn't cover here. And I think that having 2 or 3 sources of information is a really strong way for you to get a good understanding of the area. So anyway, that will form the end of that first third of the actual course. So you can see all of this here. And then next week, I will basically put up a lecture on sampling, and I'll set the midterm that week. So that Thursday on March the 1st, so let me look here. So March the 1st is this week. It'll be the lecture will go up on the Thursday. That's when I will set the midterm, and then it will be due by the following week. Okay, so you need to make sure that you log on, you take that test, and don't forget to do the other ungraded tests beforehand, because as I indicated, those are the tests that are going to let you know whether you actually understand the material or not. And the worst thing that you can do, the easiest way to fail this class, is to not do the ungraded tests, because really they're going to give you a lot of information that you need to know in order to really excel on the main midterm here. Okay, great. So that's enough background material. Let's get stuck on with the actual laboratory session. So you have the code, the Lab 4 code. It's on the Blackboard website, so you need to download it. You can then load it in your own R Studio software and start running this code. You also have the slides which go with this session. So I know it was a big one this week. I think we got up to 57 slides. And obviously we covered those kind of basic probability definitions and events. We then covered those 3 main types of distributions. So we covered binomial distribution, remember the one with 2 outcomes. We then covered the Poisson distribution, so a way to understand different event outcomes, for example, over time. And then we covered the normal distribution, so a continuous type of distribution, and we did some little tests, some work through examples on Z-scores, which, you know, I understand that's a daunting concept, but to kind of get your head around those standardized Z-scores is really important, because it helps you understand where certain values may exist within that total distribution. And I'm going to cover this now. So hopefully if you didn't really kind of understand it in the previous lecture, that's fine. Hopefully you're going to get more information now from this lab session. And I hope that by the time you finish this, you go away and you put effort into understanding it, then you'll have a really decent grasp of what we've covered here. So let's just do some basic probability to start off with. Okay, so let's say that we've got this this problem that we've got here, this problem set, and it's focusing on the fact that everybody in the world has a specific blood type. Okay, so let's just say in the US we have these 4 different blood types, so A, B, O, and AB. Let's just keep it simple. Obviously, some people have plus and negative types. Let's just keep it at those 4 types and assume that we have this distribution of blood types. So we have 45% of people in the O category. We have 40% of people in the A category. We only have 11% of people in the B category. And then we have only 4% of people in the AB category. So if you add all of them up, you should get 85 for the first 2, and then we add the 11, so we get to 96, and then we get the 4% at the end here. So this all adds up to 100%. Or in terms of the probabilities that we've got here, it adds up to 1. Okay, remember all of the probabilities are between 0 and 1. I've just interpreted them as percentages because it's kind of more intuitive to think of it that way. Okay, great. So the question is, sorry, before we begin, any person can receive their own blood type plus the O blood type. Okay, and then the question is, as a consequence, what's the probability that if you randomly chose a US citizen who's able to donate blood, that they can donate blood to a person with type B blood. Okay, so what we need to do first is we want to get the probability of people who have type B blood. So that's 11%. Then we want the probability of people with O, because obviously they're able to provide blood to anybody. And O is 45%. So now we've got these 2 probabilities. Then what we want to do is we want to find the probability that any American selected can provide blood. So we need to take the probability for somebody potentially having the B group and somebody potentially having the O group. And as you'll have caught, we're using or here in the middle. Now, remember, I mentioned this within the lecture that if we say or, then that's indicative of it being either one or another outcome. And therefore, as a consequence, what we want to do is we want to set the probabilities for all of those different blood groups. So for O, for A, for B, and for AB. So I'm going to put those into the internal memory of this particular session that we're in of R. So it's in the global console here. And then what we want to do is we want to get the probability, and basically it's a combined probability. We're using OR so we can add them together. And when we do that, we're basically saying take the O group probability, 45%, and take the B group probability, which is 11%, and add them together, and therefore that generates 0.56, so that's 56% probability that any single selected citizen would be able to donate blood to somebody with a type B blood group. Okay, so I hope that that's reasonably clear to you. I've basically just provided a second example here. So imagine that now we're focusing on citizens of India. So I've actually just finished an assessment of India, which is pretty interesting on 5G universal broadband as a side topic. So I've been doing a lot of work on India recently. But basically, imagine now we think of the blood composition of all of those citizens of India. So, I mean, America, a very large country, is 330 million people. But then India, 1.4 billion people now. So it's absolutely huge. And it's still got a rapidly growing birth rate. So it will become the largest country in the world by population in the next couple of decades. It will overtake China. China's birth rate is now static or slowing down, almost declining, likely to decline over the coming years. So India. So this is the distribution of blood groups. So they have 35% of people with an O blood group, 27% of people with an A blood group, 26% of people with a B blood group, and then 12% of people with an AB blood group. Okay, so if we add these together, these should sum up to 1. Imagine that we chose an American citizen and an Indian citizen random from each population. What's the probability that both have an O blood group? Okay, So what we need to do here is we need to get the O probability for America. For an American citizen, it's 45%, and for an Indian citizen, it's 35%. And as we're interested in the combined probability, we're going to be using AND. So remember, we did this in the first example when we focused on repeatedly tossing coin as an example, and we have probabilities on each of those. We can think of the same problem in the same way here. Okay, so what we need to do is we need to multiply these probabilities together, as we've got a probability from each population that we're selecting a person from. So let me just clear the first, oh no, we actually need those. Let me add these to the memory. So these are the O group for India, the A group for India, the B group for India, and then the AB group for India. And then what we're going to do is going to multiply the O group for the USA and the O group for India. And what we end up with is 0.1575, so it's 15.75%. So it's about 16% based on this particular example. Okay. So they were two examples for basic probability. In the first one, we were adding the probabilities together. In the second one, we were multiplying the probabilities together. And then in the third one here, now we're going to focus on an example of email spam. Okay, so just to finish off on this section, imagine that a majority of email messages today are actually spam. So generally untargeted, unsolicited emails being sent to your email inbox automatically by robots. When the spam topics are actually analysed, they're basically distributed as follows. So about 16% are financial, about 7% are health, about 7% are leisure related, about 21% are products related, about 14% worryingly is they're actually scams, spear phishing, phishing emails, for example, ransomware, and then about 14.5% fall into the other category. Okay. So what's the probability that a piece of spam that might arrive in our email inbox does not concern one of these topics? Okay, so what we're going to need to do here is we're going to find the probability of something else that doesn't fall into these topics. So one is the total number of probability, the total of all of the different probabilistic outcomes. And then what we want to do is we need to sum all of the probabilities that we've got across all of these groups, okay? And then if we subtract that value that we get from one, we'll get the probability of it lying outside this set of groups, okay? So let's add all of those different topics together, so financial, health, leisure, products, scams, and other. And then if we basically add them all together as follows, then we end up with about 81% of the emails in total coming through to our email inbox based on these different categories. Okay, so already you can start to tell that about 19% of those other emails coming through aren't related to any of these products. So then when we follow this formula through here, 1 minus the existing number of topics, we get 0.19 as the probability for any email coming through not relating to these, so about 19%. Okay, great. I hope that that was reasonably clear. I think that they are fairly simple examples. They just give you a bit of a flavour for how we would do these calculations in reality. The operations here aren't very hard. I mean, it's just summation, multiplication, a small amount of summation and subtraction. This is all simple. It's more about the logic of you actually understanding how to discern which types of operations you should be using based on the question that you're going to be set. Okay, so hopefully that's fairly straightforward for you. Now we're going to move on to the binomial distribution. So remember, this is the distribution where you just have two potential outcomes. So for every event, it either could be pass or fail, or success or fail, or 1 or 0, or yes or no. Okay, so you remember that I spoke in the lecture about the fact that this begins with bi, so that's relating to 2. So bicycle, binoculars, for example. Okay, so the built-in function here is binom, and this is prefixed with either D, P, Q, or R. So I covered this in the lecture. So the D returns the probability distribution function, P returns the cumulative distribution function, Q returns the inverse of the cumulative distribution function, and R returns random samples from a binomial distribution. So based on that, we can look up the help menu, which is always good to read for any function. So if you look in here, we have the binomial distribution function, which is from the stats package. Here it's actually an inbuilt R package, provides you with those different types of functions that I mentioned before. And the usage here provides you also with the actual arguments that you can provide to each one of these 4 different types of binomial function. You can provide a vector of quantities here, or a vector of probabilities, or the number of observations that you want, you can provide the size, so the number of trials, 0 or more, and then you can provide the probability of success for each of the trials, and then you can specify whether you want this to be the logarithm, or whether you for which part of the distribution you actually want to specify. Okay, so I touched on this previously about why we would want to specify lower tail equals true or false within the lecture, but this just provides you with a bit of an extra overview. Okay, let's apply that function that we've already covered so you get a good understanding for why we would want to do such a thing. So let's return to the vegetable grower problem that I covered previously. So it's actually also on page 82 of McGrew et al. So hopefully you've got that book now and you're reading it. What's the probability that a grower can actually meet the requirement for irrigating only 1 in 5 years? So a farmer wants to select a new site, and there's a bit of uncertainty around how often that new site may actually need irrigation from a source where the farmer basically has to pay for the water potentially, also definitely has to pay for the electricity to pump the water, and that can be very expensive. So let's go back to that particular example, and then we can use some of the data that we generated there. So you'll remember that in that particular example, I gave you a very simple set of data that could be placed into an Excel spreadsheet, and I gave you the formulae that you could use to generate each of these, both for the denominator and the numerator. So the numerator and the denominator, just to do it logically. So you can always tap this into your Excel spreadsheet if you want to get a decent understanding for it. I think the key point is that N stands for the number of trials, P stands for the probability of a given outcome, and X is the number of times the given outcome occurs within the number of trials, okay? And then pretty much everything else we can calculate ourselves. So if we've got those inbuilt, those parameters that we entered into the global environment, we can then run the binomial density function here, providing it with the X, the N, the P. And what it's returning is, so we specified that we wanted an X value of 5, so the number of times an outcome can occur. And we also stated that the number of trials is 5. So when we enter this in here, what we end up with is these particular return probabilities. And actually, you'll remember these probability values because we did end up actually plotting them afterwards. So you can start to see that this is the shape that we would get if we plotted these probabilities. So that's how you generate this set of probabilities that I basically did using that Excel spreadsheet by hand. It's a hell of a lot easier when you just can use the function as I've shown here. So hopefully that's easier for you. We can plot these, and again this plot, as you can see here, is going to end up being very similar to what we showed before. So sorry, I'm just trying to make this so that we can view it side by side. And there we go. So you can see that these probabilities here for 0 years, 1 year, 2 year, 3 year, it follows this exact shape that we've managed to generate. So that's good. That means that what we did in the class does actually match the inbuilt function, and therefore there's consistency between the two, so that's important. So now we've plotted those probabilities, hopefully you have an understanding of what we're doing here. the actual original question was related to the requirement of irrigating 1 year and 5. So you've got those probabilities here. So the probability for irrigating 0 years, for 1 year, 2 years and 5, 3 years and 5, 4 years and 5, or 5 years and 5. Okay. So remember that we basically wanted to get this probability here. Okay, so let's move on. So suppose we want to know the probability of 0, 1, or 2 years. So this is the total probability of any of these outcomes occurring, and we can just manually calculate this. So if we, sorry, my bad. There we go. If we actually just go into the vector that we created here, so if I just run this, remember that's got these values here. So for 0 years, 1 year, 2 years, we can then just index into that vector. Remember, as I showed you before, we just need the square brackets, and then what we're saying here is give me the first value in this vector, or give me the second value in this vector. All this is doing is saying go into probability x that returned up here and get me the third value. Okay, so the key point here is that it's got the square bracket. That means we're indexing into that vector. And when we add them together, we end up with 0.96. 82413. So it's 96.8% probability that any of these outcomes occur. Okay, so 0, 1, or 2 years worth of irrigation. So that's the manual calculation. My point in doing this was that I can show you how we do it using a function now. So you don't have to worry about doing that type of manual calculation. It's fine if you want to do it that way. It's good for you to understand it. But actually, if you just wanted to get the cumulative probability for those for that particular problem that you've been set, then you can use the p binomial function here, and we're saying we want up to 2 years, so 0, 1, or 2 years. So that's what we're providing to the function, and we've got the number of trials and we've got the probability. So then when we run this, we end up with the same value that we were getting before. Okay, so let's just go back. Let's go to the p binom. That's what we've entered here. So we've entered q. So we've entered it's a vector of quantiles. So we've basically said give us. We've allocated. We said we want up to 2 years worth of probabilities. We've given it the size n, and then we've given it the probability for it occurring in any year. Okay, so hopefully that gives you a bit of understanding for how we use that particular function. We then want to start calculating the probability of needing irrigation for 3 or 5 years. So that's fairly simple. We could actually get that by just taking the probability of irrigation for no years, the probability of irrigation for 1 year, the probability of irrigation for 2 years, and the probability of irrigation for 3 years. And then we could just add them all up and subtract them from 1. And that would get us the probability of needing irrigation for 3 of the 5 years. Okay, and that's actually really small, thankfully. Okay, and then we could also calculate this using the function. So if we just went for p binomial and we just called this based on these arguments that we specified in order to answer this question, we could just subtract that result from 1 in order to obtain exactly the same results that we were able to achieve by doing the manual calculation. Okay, so for calculating the probability of needing irrigation for 3 of the 5 years. Okay, so I think the thing for me just to emphasize there, remember, is that when we're talking about the number of years, remember that we started the x vector here. We started it at 0 and it went to 5, so we had 6 values, and that's why when we specify this d binom here, it's returning 6 values. And then when we're indexing here, remember this is focusing on the position of each of those items within the actual vector. Okay, so I just want to emphasize that there's a difference between the actual number of years requiring irrigation and the location of certain probabilities within that vector. Okay, so we're doing different things here, so it's just important to remember that. Okay. Great, so that's how you would basically do this using the cumulative distribution function. You could also use the cumulative distribution function, but rather than going 1 minus in order to get that probability 0.02, you could just use the lower tail equals f. Okay, and that would give you the same value. So what we're doing here when we run this particular function is we are getting the lower tail, and then when we say lower tail false here, it's giving us the complement of that probability. Okay, so it's giving us the upper tail. Okay, let's move now on to Poisson distributions. So here we are actually going to calculate the formula directly, and if you look in McGrew et al., you can look at page 87. So this example is based on the probability of the expected number of days with heavy snowfall in Flagstaff, Arizona. How many heavy snowfall days are actually likely? So when I first read this, I didn't know that it snowed in Arizona, so I had to look that up. Obviously, it's quite high altitude in Flagstaff, and that's why there's occasionally snow. I guess with the crazy weather that we've been having in the last week or two, and what's been going on with Texas with the giant freeze, unfortunately many people losing power, it just goes to demonstrate that these extreme weather conditions occasionally can sweep really far south. Even if you're living in the middle of the desert, you might occasionally get snow. It would just be a very rare event. Okay, so that was quite interesting to look at how many days may get snowfall in Arizona. So first of all, what we want to do, and in fact, let me go back to the equation so you can remind yourself. This is basically what we want to produce. It's the Poisson distribution equation. So we want to find the probability of x occurring. We need to get the lambda value, which is the mean frequency of the event, raise it to the power of x. So again, it's the frequency of occurrence. Divide it by the natural logarithm raised to the power of lambda multiplied by the factorial of x. Okay, so to get that x value, we're going to concatenate values between 0 and 6. So when I print x here, we have a vector of 0 to 6. And then we're going to actually allocate our lambda value, which we know is 1.8. It's the mean frequency for per winter of heavy snowfall days in Flagstaff, Arizona. Okay, so we've got the lambda value. So the value e for the exponential is a constant that's produced by the exp. So it's this exponential function is based on the natural logarithm. Remember that the natural logarithm of x is the power to which e needs to be raised to equal x. So we can just use the exponential function here. It's an example for 2, or the exponential function for 1. Essentially Euler's number is e equals 2.71828. Okay, so we know what this value is, and that basically means that in this particular case, as 1.8 is our lambda value, essentially we can get this particular value here by raising that exponential value, so 2.71828 to the 1.8 occurrence value that we have. Okay, so that results in 6.04965. Okay, we could just do that using the function. So here we go, I've specified it, and that's the easy way to do it, I guess. We now able to actually specify that full function. So we have the lambda value for the mean frequency of winter weather days. We have the x value up here for all of those different occurrences for heavy snowfall days, the frequency of occurrence for heavy snowfall days. And then we can raise the lambda to the power of x, and we can divide all of these values by the exponential of lambda multiplied by the factorial. Okay, when we do that, we end up with a set of probabilities for those different outcomes. Okay. So the built-in functions are just like the ones that we've shown before for the Poisson. So previously I showed you for the binomial. If you look in the Poisson distributions, basically exactly the same. So you have this density Poisson, the probability Poisson, the quantile Poisson, the random Poisson. Okay, so we can actually use those functions. So if we just provide the number of x values that we have, so remember x is the frequency of occurrence, we want to find that for up to 6 different days. We can provide it with that vector here, and we provide it with the lambda. So this is this particular function here with these two arguments, x and lambda. And then when we print that, we end up with those probabilities. So the probability of there being no snow, so this is the mean frequency per winter of heavy snowfall days. How many snowfall days are likely? Well, 0 snowfall days, there's 16.5% of that. 1 snowfall day, there's 29.7%. 2 snowfall days, 26.7%. 3 snowfall days, 16%. 4 snowfall days, it's about 7%, and then 2%, and then 0.7% for the final one. So this is providing us with probabilities for that number of snowfall days that we might expect. Okay. So that gives you an example of how we generate the actual probability for those different values. Okay, using this kind of theoretical math formula, and then here what we've done is we've just hacked it out. Basically, we've hacked it out using R manually, and then I've shown you exactly how to use the inbuilt function in order to just get the set of probabilities for those different events that we're interested in. Okay, so hopefully now you've kind of got an understanding of how we've generated that, and you can just use the function in the future. So let's solve this problem. The number of arrivals to a wilderness park is found to be Poisson distributed with a mean of 2.5 camping groups per day. So on a particular day during the summer, what is the probability that no groups arrive at the park? Okay, so let's just imagine that we're in Yosemite, we're on our holidays in California. Forget that you have to apply for a permit to have permission to camp in the park and walk in the park. Imagine that we were just able to turn up whenever we wanted. And essentially, we're in the wilderness park, in the national park, and we're interested in the probability that no groups will arrive at this park. Okay, so we are going to provide the lambda value to the Poisson density function, which is 2.5, as we've already stated, the mean occurrence per day. And then imagine that we provide it with a value for 0 for the vector of quantiles, or in this case just the single quantile that we're interested in. And that's going to provide us with a probability which relates to the likelihood of no groups actually arriving in the park at that particular time. Okay, so essentially that's it's 8%, it's 0.082085, so there's an 8% chance of no groups actually arriving in the park. Well, actually, maybe what we want to do is we want to get the probability that there's between 1 and 3 groups arriving, okay, inclusive. So this is the case where x is going to equal 1, 2, and 3. So what we're doing here, remember, all we're doing is we're concatenating 1, 2, and 3 into a single vector. And then once we've got it in the single vector, we can just provide it here as the x value. So that's why x is described as a vector of quantiles, because although I gave it a single number, a single integer in the previous example, here we can actually provide it with a vector. So that's what we're going to do, and it's going to return the probability for those 3 examples. And we provide it with the mean frequency of occurrence, which is 2.5 groups arriving per day at the Wilderness National Park. And this is basically the set of probabilities that we get returned for 1 group, for 2 groups arriving, for 3 groups arriving. So it's 20%, 25%, 21%. Okay. So that only provided us with the individual probabilities for each of those different outcomes. What if we actually wanted to get the total probability? So we basically need to actually sum those different probabilities that are returned to us. So we're getting the probability of 1 group, 2 groups, and 3 groups. And all we need to do, therefore, is we just need to sum them together. So you could just do this individually, as I kind of demonstrated in the lecture. Here we just did it individually, one at a time. Or here what's quite nice is that we're actually providing the function with the vector. It's returning a vector of those probabilities, and then we're just using the sum function, which is just inbuilt R, to just sum all of those probabilities together, okay? When we do that, we end up with 67.5% probability. And essentially that's because we're summing 0.205, 0.256, and 0.213. Okay, so that's 20 plus 25 is 45 plus 21. So we're getting 66 plus all of the remaining decimal points. So basically you're getting this value here, 0.6754911. Okay, so that's the probability for how you work out that particular problem. Let's move on now. So you'll remember that what we were doing in this lecture is we covered the binomial distribution and the Poisson distribution, and now we're going to move on to our best friend, which is the normal distribution. So remember, it's called the Gaussian distribution, or the bell-shaped curve that we're interested in. It's continuous, so it's for continuous data, as opposed to the previous two distributions which we looked at, which focused on discrete integer values. Remember, I said before you can't have 2.5 people or 4.5 hurricanes, so it's just integer values of 1, 2, 3, 4, 5. And obviously this is going to be different now that we get into continuous data, because you can have an infinite number of values. You can have as many decimal places as you want on any of your numbers. So the formula for calculation is difficult, so we don't want to use it. So we're going to use a standard normal table. This is just standard practice in statistics, just so you don't have to go through and work out the probabilities. That means that we have to convert our distribution to one where the mean is 0 and the standard deviation is 1. We then use the standard normal table. We use we then turn to the standard normal table, and we use a value from that new distribution called a z-score. So remember, I was just saying that we're standardizing all of those values. So it doesn't matter what the underlying values are, we're going to express the distribution of those values in the standard deviation. Okay, so it's going to be in the number of standard deviations either above or below the mean. So to get our z-score, z is equal to the particular value, which we then subtract the mean from, and we divide by the standard deviation. So traditionally, I mentioned we've been using z-score tables. Okay, let me just tap this into Chrome. So take a look at this website. It's pretty nice because it provides you with quite a nice description as to how to use z-score tables. So it provides a detailed step-by-step explanation. I think it's pretty good. So they say here, 50 randomly selected volunteers, as just one example, took an IQ test. Helen, one of the volunteers, scored 74 from a maximum possible 120 points. The average mu value was 62. The standard deviation was 11, the sigma value. How well did she do on the test compared to the other volunteers? So step one for understanding this is that we need to convert this to a z-score. So we covered this within the lecture. So the z-score is equal to x minus the mean of the population, in this case, divided by the standard deviation for the population, sigma. So in our example, basically it's 74 minus 62 divided by 11. So this is the value that Helen got. Helen's very clever. She's above average IQ. We subtracted the mean, which is 62, and then we divided by the standard deviation, which is 11, and that gives us 1.0909 reoccurring. We then can round this to 1.09, which is standardized. Okay, great, that's fine. How do we actually use the z-score? So basically what we want to do is we want to get the standardized score, which we've got, but then we need to look up the area. So just think of this as the probability using the Z table. So we need to find the first two digits on the left-hand side of the Z table. In this case, that's 1, 0. And then we look up the remaining numbers across the table. So you see here we can go down the axis for the first two numbers. We're in the 1, 0 axis here for Z. And then we need to go and find on, so that's the y-axis, and on the x-axis we basically need to go and find the other digits out of our particular z value that we got, which in this case is 0.09. And when we do that, what we actually get is 0.8621, which translates to 86.21% of the data data that we have in the distribution fall below Helen's IQ. Okay, so that means that basically there's 86% of people below her who she's smarter than, but then there's also about 14% of people above her who are actually cleverer than her. Okay, so that's the whole point of using this standardized Z-score approach. It means that we can check in the Z table the area corresponding to that Z-score. And that means that we can then say something comprehensive about where she sits within the distribution or what the probability of a future score may be. So I think the key point, and I'm going to emphasize this, is that you need to know what the Z table actually measures, okay? So you need to know if that's going to cover all of the area underneath that, that point that you've got, or if it's just the point from the mean, okay, to that point that you've got. Okay. So draw a valid conclusion. This is what we did. We had 1.09 here. We then checked the area under this value, which was 86.21%, and so the area to the left of the z-score. And that means that she's cleverer than all of these people here, so that's 86%, and she's less clever than the 14% that sits above her. Okay, so take a look at the website. I rate it. I think it's good. They provide the z-score calculator as well. Sorry, I don't know why I'm being spammed with ads. I think that's obviously because it's a free website, so they're trying to milk as many ads out of users as possible. But you've got the how to use the z-score table, the z-score calculator, calculate the z-score. I think the key point, as I'll emphasize in the R code, is that when you're in the back of your book here, this provides the area from the value that you have to the mean, so you need to make sure that you're recognizing exactly what those values are measuring. So see the example in the book on page 95. We've got a 40-year annual precipitation record for DC. Let's make various probability estimates. What's the probability of annual precipitation exceeding 48 inches? So first we need to calculate the standardized Z-score. So we know the mean is 39.95 inches. The observation that we have is 48 inches. The standard deviation around the mean is 7.5 inches. So to get the Z-score, we need to subtract the mean from the observation value that we have, and we need to divide it by the standard deviation. When we do that, we get a Z-score of 1.073333. Okay? So hopefully that's reasonably clear for you now. You can look up the corresponding probability of the Z-score in the Z table. Just make sure you know exactly what you're measuring. So in the book, that Z-score is going to be 0.3577, which is the distance to the mean, okay? Rather than the whole distribution that falls beneath that value, okay? So you'll remember that when I was here, I was talking about all of the values that fall under here. That was 86% in the previous example. Remember that you need to be aware if you are taking all of those values beneath that point, or just the level of values that fall down to the mean value. Okay, so we can, as a consequence of the value that we get from our table in the book, we can subtract 0.5 for the final probability. And this provides us with the probability of over 48 inches, okay? So only 14% is, so we 0.1423, we have only a 14% probability that the level of precipitation that's going to occur is actually going to exceed that 48 inches annual precipitation. Okay, and you can see figure 6.3 in the book on page 95 for any graphical interpretation that you may want. So I just go through here in the code, and I basically provide a bit more of an explanation about how you derive this score. I'm not going to go over it yet again, but read through it and make sense of it, and then just be aware of how you use the standard normal tables. Okay, so you can go and take a look at the normal distribution function that we have here by looking at the help menu. Again, we have those 4 different types of functions that are available for this one particular distribution. So the density, the probability, the quantile, or the random number, set of numbers from that distribution. And therefore, you can just use these in a similar way to the way that we used them previously. So the form of the function you should understand. You've got this set of arguments for x, the mean and the standard deviation. Since we have a z-score already, you can omit the mean and the standard deviation arguments. So when we actually place our z-score into the p norm, we're getting the 0.85 probability here. So this is what this is saying is 85.84392% of those data values are falling underneath the data value that we have. We don't want the number of data points beneath that. We want the number of data points above. So an indication of the probability of values falling above that point. So therefore, what we can do is we can get the complement of that probability. We can subtract the value that we get from 1, and that provides us, it reproduces the value that we got above when we did it manually. And that's indicating that there's a 0.14 probability that any year with precipitation will exceed that 48 inches value, what you can interpret as 14%.15608 probability that it may exceed that value. So you can take a look at that in more detail. Now I'm just going to provide a little bit of an overview of the quantile. So here, I suppose the question's not what probability, but what is the number that goes with this amount of the probability, okay? So in effect, we're reversing the process here. So given a probability, find the z-score. So you can look up exactly the arguments for using this function. So just think of p at this point as the place where 90% of the values fall above, okay? So we can call p 0.1. So if we then get the z-score for this, what that's basically saying is that value is minus 1.28 standard deviations below the mean. Okay, and that's giving us the z-score for that particular probability that we're getting. So imagine we've got a z-score. But what does that actually tell us about the amount of precipitation that we have? So we can go back to the equation for deriving the z-score and substitute the values that we have and then solve for the xi observation. So in order to do this, we have to do a little bit of algebra, basically. So we need to rearrange the equation. So if there's anything that you get from today that you might be tested on, be aware this is something you might be tested on. So, for example, you might be given the z-score, and then you might be asked to actually then substitute in the values that we have and solve it for the observation that we've got, okay? So the equation that we need to do that is that the observation value will be equal to the mean plus the z-score times by the standard deviation. Remember, the z-score is expressed in standard deviations, okay? So if it's 1 above the standard deviation, and the standard deviation is 5, then that value in the brackets is going to be 5. And then if we have a mean of 30, we're going to add them together and we'll get an xi value of 35, okay? So it gives you a way to convert the z-score into an actual value that sits within our distribution. And this is the type of thing that you'll be actually tested on. Okay, so let's just go through that again. The x-bar is 39.95 for the example that we had. The z-score is minus 1.28, and we're multiplying that value by 7.5. When we do that, we get minus 9.6. So obviously we are going below the mean here, it's a minus value. So when we subtract minus 9.611637 from the mean value that we have, that's how we get the 30.33836 inches of precipitation that I mentioned previously. Okay. So let's just finish off now. I think I touched on loops before, but it's just important for you to understand how loops actually are used within the R code. So some functions use loops behind the scenes in R when dealing with different vectors. So if we call the standard deviation or the sum, for example, R will use a loop to obtain the answer. So imagine we're concatenating 1, 2, 3, 4, 5 into a vector. I've shown you what that looks like down here. If we calculate the standard deviation, if we calculate the standard deviation here for new, then we can get 1.58 as the standard deviation. We can also get the sum of these values, which is 15. Okay, so it can use loops behind the scenes in order to make estimates of particular values, and we can use the function here, so it's kind of easier. You don't have to write out exactly how this works behind the scenes, but I'm going to show you now so that you're aware of exactly what it's doing. And then maybe in the future, if you need to do advanced work, then you know how a function works, you can build your own functions, and then you get into the highly creative business of computer programming. So let's just say that the summation value to start with is 0, so we haven't summed any values, it's just 0. And now what we're going to do is we're going to create a loop. And a loop always starts with a for statement. This just basically telling R that you're going to create a loop. And then when it sees that for written FOR, it knows that it's expecting a loop. And then what you're going to say is for n, and n can take on any number between the sequence 1 to 5. And it's going to basically then say, okay, generate, in sequence, generate a number between 1 and 5. It's going to start at 1, and that's going to be n, and then it's going to run through everything that's in the curly brackets here. So it's going to take the summation, which is 0, and in the first instance, n is going to be 1, and then it's going to say 0 plus 1 equals 1, and then we're going to print it. And then the next iteration, the summation will already be 1. The n will then take 2, so it'll be 1 plus 2, so we get 3, and we're going to print it, and we're going to get 3. So basically when we run that, we get this list of numbers here. So these numbers printed to the console. So the results shown manually, so this is exactly what we're doing. We're going 1 equals 0 plus 1, 3 equals 1 plus 2, 6 equals 3 plus 3, and it's just iterating through everything that's written within the curly brackets, but it's basically providing a new value for n each time that it runs through, and so the summation value is holding on to the value from the previous iteration. Okay, so in the first iteration it's 0, in the second iteration it's going to be 1, in the third iteration it's going to be 3, and that's how we end up adding n onto that existing number that's been calculated. Okay. So let's look again at how the binomial distribution changes with plot size n. So we're going to plot multiple lines on a single plot. So we can say that the n value is 5. We're going to generate a set of trials between 0 and 20. And then we're going to allocate a probability of 0.1. And then what we're going to do for this is we're going to make a fancy plot, is we're going to specify the line type as 1 and the point character type as 1. And we're going to basically get all of the binomial probabilities for all of those different potential outcomes that we specified up here. And now for the plot function, we can give it the number of x values that we wanted. We can give it the actual bin variables that we've got, and we can specify the years and the probability for the x and y axis, and we can specify the limits of the plot. Okay, so this is just plotting those initial probabilities. You can see we printed them here. We've only got values for those first 5 really, so you can see it dropping down quite significantly. And then we can actually add in lines for that particular bin. So this is just for the very first example, providing a line that we've drawn based on the probabilities where we had these specific specifications. We can actually use a loop, essentially. So we're just going to sequence through where the n value starts at 20 and goes all the way up to 10, sorry, all the way up to 100 in intervals of 10. You remember the sequence basically takes either two numbers, so a starting point and a finishing point, or if you put in a third variable like this, it's saying go between my start and my finish in 10 units at each time. And I'm going to print the n each time, and I'm going to add a value to the line type and add a value to the point character type. And we're going to calculate the probabilities. We're going to generate the lines for the plot and the points for the plot. And then when we do that, and we add the legend, and we add the title, we get this funky looking binomial distribution plot where for each changing value, so let's just go back here. So each time what we're doing is we're providing the n value here. So this was previously 5 in the first iteration, and then each time we add a new set of values to it, so starting at 20, going up to 100 in intervals of 10. And that's how we get this really beautiful plot, and it's kind of nice. You can see how the shape of the distribution, so the probabilities of those different distributional options that we specified change as we start to vary those parameters. And you can see that this is kind of quite similar to the binomial distribution that we used in the first example in the lecture. And then actually by the time we get down to this last point here, what we're actually getting is quite a fairly standard normal distribution shape. Even though it's binomial, I'm just saying that the bell shape is fairly similar. Okay, great. So this gives you a bit of an example of how the distribution changes as we change some of those parameters, and using a loop's a nice way to kind of understand how the distribution changes. Okay, great. So I don't want to overcomplicate things. I know that this has been a kind of horrendous week for the amount of content that you've had to take on board. I'm afraid there's no easy way around it. It's hard to learn, and you just need to make sure that you're writing it out and revising it. Do whatever it takes for you to actually absorb that information. But I'll leave it here. There will be an assignment this week that you need to make sure that you complete and then submit the following week. Let me know if you've got any queries or questions, and hopefully by the time we finished off this week, then you'll be kind of fully ready to grasp the following week at a reasonable level, and you can then succeed at the midterm. Okay, so thank you very much, ladies and gentlemen, for tuning in. It's been nice to see you all, and I'll see you all very soon. Goodbye.